Okay, we'll begin. Are there questions?
Sir,
Yes, go ahead, please.
sir, I have a question from the previous lecture, that is lecture 24, page number 208.
Okay.
Yes,
Yes,
sir.
okay.
Sir, here the expression of G tilde P1 P2 that we are getting uh, in this prescription, the earlier when we learned how to calculate G tilde P1 P2, for example, we drew the Feynman diagrams and we excluded the bubble diagrams, and then we calculated the in the position space, and then we took the Fourier transform in the momentum space. So in that prescription, the whatever G tilde P1 P2 we get, this is the same as this G tilde P1 P2 that we are getting here.
Yeah, it's the same. So basically what it is doing is that it's just reorganizing the diagrams. See, if you look at the earlier prescription, right?
Yes,
These are the kind of diagrams we'll be getting in G tilde, right?
yes,
Okay, all kinds of diagrams. I mean, because these are not bubbles, right? Bubbles are disconnected.
yes.
So these are all part of G tilde. And what we are saying now is that we'll reorganize this sum, right? We have to sum over all these diagrams.
Sir, but in this prescription, we discard this 1 point irreducible functions. But in the previous prescription, we included all diagrams, all the diagrams, excluding only the bubble diagrams. Only.
Yeah, okay. So the point is, it's not in G tilde, we are not excluding this, right? We are defining a new quantity, this I sigma, where you are excluding the one particle reducible diagrams.
Okay.
So I sigma contains the sum of all these.
Okay.
Okay. So G tilde contains everything. Okay?
Okay.
But the point is that whatever G tilde contains, right, can all be summarized. Once you have defined I sigma as sum over one particle irreducible diagrams like this, then G tilde can be obtained by simply repeating sigma.
Okay, so G tilde P1 P2 can be done by this sum of this infinite series, and here we get in this G tilde P1 P2 there is contribution from both 1p I reducible and 1p I irreducible both.
That's right, exactly.
Okay.
Yeah. So G tilde P1 P2 has not changed. It's exactly the same as what we had before. We have just reorganized that sum in this way.
Okay. Okay.
Is this point clear?
Yes. Yes.
So every diagram here, right, contains that. Once you pick any diagram in sigmas, right? You can pick, for example, this one here and this one here. That will be a particular contribution to G tilde, right? Where the first entry is this one, the second entry is this one, right? Maybe, yeah, this one, for example, right? This corresponds to picking this diagram for the first sigma and this one from the second sigma.
Yes.
Is this clear?
Okay. Yes. Yes.
Okay. Okay. Any other question? Okay. If not, I'll proceed. Here. Okay, so let me then begin by reviewing the setup that we introduced yesterday. Okay. So earlier we had calculated the probability of scattering, okay, and we saw how to relate it to experimental, what you can actually measure experimentally. Okay. So today we are going to use the same S matrix theory to calculate decay probabilities. Okay, so if you have an unstable particle, you may ask what is its lifetime, right? That's a crude information about the system, but you can more generally, I mean more specifically, you can ask that when the unstable particle decays, imagine that you have many of these unstable particles and then they decay. Each decay will produce something, and there'll be a distribution of those decay products, right? If you place a detector, then you will find that maybe it's more probable that particles come out in one direction and rather than the other. So all those questions you want to study in this process. So the setup that we had was to consider a field theory which has two scalar fields, which are denoted by phi and chi. And we took an action of this kind. So this is the standard kinetic term for the phi, okay, the kinetic term plus the mass term. This is a standard kinetic term plus a mass term for chi. And here is a coupling between chi and phi. Okay, so chi pi square. So just from this coupling, it's clear that when you draw Feynman diagrams, there will be a 3-point function in which there is one chi and two phis. So that will give a contribution to the S matrix or Green's function with one chi and two phis. So this allows for a possibility of decay of a chi into two phis, okay, because that S matrix element is non-zero. But of course, this is only possible when m chi is larger than 2m phi. Because if we go to the center of mass for chi, then by simple energy momentum conservation, okay, the two phi particles will have to carry opposite momentum, which we call pi plus minus q. And then the energy conservation will tell us that m chi should be equal to twice square root of m phi square plus q square. And if you consider a general Lorentz frame, where the chi particle will have some momentum, which I call p, and the phi particles will have some momentum q1, q2. Okay. And then you have to satisfy the momentum conservation, that is p equal to q1 plus q2, and energy conservation, which is square root of p square plus m chi square, should be square root of q1 square plus m phi square plus square root of q2 square plus m phi square. And it is clear that this decay process, okay, because there is only one incoming chi and two outgoing phi, this should be decay. It should be described by some process like this, that you have two phi in the out state and one chi in the in state. So I have denoted this by chi p in. Okay, so now the label includes not only momentum but also what particle you have. And similarly, the outgoing levels include the momentum level as well as what kind of particle you have in the final state. Now here we pointed out a problem, okay, and we'll in fact encounter it today again as we start doing the calculation, okay, that this state chi p is not strictly an in state. Okay, and the reason that it's not strictly an in state is because it cannot exist forever, right? An in state by definition is a state which you can evolve in the far past, okay, and it becomes a well separated particle, okay, from the rest that lives forever. But if chi particle has a finite decay probability, okay, if it has a finite half-life, then of course this cannot be true because it couldn't exist forever. But as I said, we'll ignore this problem for now, okay, and see what we can get. Okay, eventually we'll run into this problem again. Okay. And so the fully systematic procedure for calculating the decay probability or the half-life of this chi particle is not what I'm going to describe today. Okay, but what I'm going to describe today works fine if you are only interested in the first order contribution to this decay probability. So this I think I have already said. So this can be calculated, of course, by the 3-point Green's function as before. And the question will be how to translate this into something that we can physically measure. And just to make things general, okay, here I am considering the case of chi particle decaying into two phi particle. But you can also consider a general process, okay, where say the chi particle decays into m phi particles. Okay, this m is a number, not a mass of anything. That chi particle decays into m phi particles with some momentum q1 to qm. And this again is of course possible only if m chi is larger than m times m phi, because again you can go to the rest frame of chi and you can see that the energy conservation tells us that the total mass of chi must be larger than the sum of the masses of the decay products. Okay, so our goal will be now to calculate this decay probability. But are there any questions about the setup?
Also,
yes.
When an electron throws out a photon to lower its energy, do we call that decay?
No, see, electron never throws out a photon to lower its energy. You would have called it decay if it could happen, right? But it cannot happen simply by the energy conservation again, right? Because you can go to the electron rest frame And in
Yeah.
that rest frame, you can see that it cannot decay into an electron and a photon.
No, but multiple photons maybe. I don't know.
No, multiple photons is even less less possible, right? It's once something is not possible, it's not possible, right? Yeah, multiple photons will require more energy, right? I mean, how will you produce multiple photons? Because again, you go to the rest frame of the electron, right?
Yeah.
So that the total energy is m, right? M electron.
I mean, in in an atom, when we excite or de-excite electrons, it absorbs or releases photons only, right?
Okay, but there you are talking about a bound electron, right?
Yeah, yeah, bound states. Yeah.
Yeah. So that's not a decay process. I mean, that you can call this a decay of an excited atom, not of an electron,
Okay.
right? So excited atoms are like unstable particles,
All
and
right.
they decay into a photon plus a lower energy atom. So that you can certainly call a decay process.
I see. Okay.
Yeah, but it's just that a free electron cannot decay.
So even those excited states are not, I mean, initially we did say that bound states aren't that well in QFT. We cannot represent them well.
Well, the bound states, the fact that you cannot represent them well is a technical problem.
Yeah.
It's not a problem of QFT per se, right? Its perturbation theory is cannot see the bound states.
Yeah, yeah.
But bound states are as good elementary particles as usual elementary particles, right? In a strict sense. That you can imagine that you have a different formulation of electrodynamics in which hydrogen atom is the fundamental particle.
Yeah. But the only problem will come when we consider excited states of hydrogen atom. That will be unstable.
Yeah.
So the same chi particle problem will come.
Exactly.
Okay.
Yeah. So if you want to do a scattering experiment, for example, right, with excited state of hydrogen atom in the initial and the final states, those are not strictly in and out states.
Yeah.
And that you have to keep in mind. Okay. Although, as I said, as long as they are long lived, right, as long as the decay probability is small, you can approximate it as in and out states. Okay, by using appropriate approximation in which this decay, the half-life goes to infinity, and then you work to first order in perturbation.
Yeah.
Are there other questions? Okay. So we'll proceed as before. Okay. So we'll describe the in state again in terms of its wave function. Okay. We'll take a normalized in state. So in state we'll write as integral dq p over t 2 ep f tilde p. This is the wave function in the momentum space times chi p. Okay. This is the momentum eigenstate in space momentum in state momentum eigenstates. And we will normalize f tilde in the same way as we did yesterday, okay, because you want the state to be normalized, right? So once you normalize f tilde this way, then the state chi f has unit norm. Okay, so that reflects the fact that you are talking about one particle in initial state. Okay. So here the only difference from what we did yesterday was that yesterday I had two initial particles. Now I have only one initial particle. And we will take the peak of this momentum space wave function to be at some value, which I'll call k. Okay, in this case, the position space wave function is not going to play too much of a role. So with this, we can again write down the probability of finding m5 particles with momentum q1 to qm in some range r. And that is given by an expression that is very similar to what we had yesterday, okay, except that in the in state, you have only one particle instead of two particles. Okay, otherwise, it's the mod square of the S matrix element integrated over the momenta of the final state particles. And we use again the Lorentz invariant integration method because that's the way you have normalized our states. Okay. So now we are going to parameterize the S matrix element in terms of m in exactly the same way that we did yesterday. Except that in this case, of course, there's a forward scattering term, right? Because the initial state has a chi and the final state has phi's. Okay, so there is certainly no forward scattering. Okay, so S matrix and P matrix are the same up to this factor of I. And then in the expression for the P matrix, we extract out this 2 pi to the 4 delta 4 sum over Qi minus P factor, okay, because this is the energy momentum conserving delta function. Then we also extract out this factor of 2 pi to the minus 3 times m plus n by 2, which is just a convention, but it's a useful thing to do. And then we have the matrix M. We have the M, okay, which is a function of the incoming and outgoing momenta. And here, strictly, I should have also written phi here and chi here. Okay, but just to shorten our expressions, I have just dropped the phi's and the chi's. But it's understood that the M that you're talking about is one incoming chi and m outgoing phi's. So we basically substitute this in the expression for P. And let's see what we get. So we have these integrals. This is the same as this. Here, because you have mod square, you have the product of the original term and its complex conjugate. So the original term is written as an integral. Okay, this is written as an integral. The complex conjugate is also written as an integral. Okay, because of this. So I have written those integral d cube p over 2 p, d cube p prime over 2 p prime, f tilde p, f tilde p prime star. Then you have two factors of this. So I times minus I, of course, gives you 1. So this doesn't do anything. So you have two factors of this, which I have written as 2 pi to the 8, and then one delta function here, sum over Qi minus p, and another delta function, sum over Qi minus p prime. Okay, p and p prime are the momentum levels for these f tilde and f tilde star. Then you have the square of this, so 2 pi to the minus 3 times m plus 1. And then you have m q1 to qmp and its complex conjugate, right, with p replaced by p prime. Okay, is this clear so far? Okay, so now we proceed as yesterday. Namely, we use this first delta function to replace the sum over qi by p in the second delta function and see what we get. So what we get is delta 4 of p minus p prime. So delta 4 of p minus p prime is, of course, delta cube of p minus p prime. This is the usual momentum delta function. And then delta 4 of p0 minus p0 prime. But of course, p0 and p0 prime are not independent, right? Because p0 is the energy of the in state, right? So it's given by EP. And this is given by EP prime. Maybe I should have written square root. This EP and EP prime refers to the chi particle energy, right? So EP, for example, is square root of m chi square plus p square. And this is square root of m chi square plus p prime square, because these are the initial state energies, right? Is this clear? Okay, but now you see that you have a problem, and this is the problem that I had mentioned earlier, that because delta q of p minus p prime sets p equal to p prime, here in the argument of delta function, we have delta of 0. This problem didn't arise yesterday, because here you had delta cube of p1 plus p2 minus p1 prime minus p2 prime. And here you have delta of ep1 plus ep2 minus ep1 prime minus ep2 prime. So you could adjust p1 and p2 appropriately to satisfy both these delta functions. But that's not possible here. Okay, when there is a single initial state, then this delta q of p minus p prime will automatically make this 0, the argument 0. So then you have to deal with this delta, with divergent factor, right? Delta of 0. And the way we deal with this is to note that the way these delta functions arise in the first place. Okay, if you go back and say why did these delta functions arise in the first place, right? these delta functions arise typically in trying to take the Fourier transforms. That when you take, for example, a Fourier transform of things like e to the it times p0 minus p0 prime, you will get a 2 pi times delta p0 minus p0 prime. Okay, that's the way that these delta functions arise. So now that we are running into trouble with delta of 0, so let's go back and rewrite this as the integral again, and then try to see how to evaluate this for p0 equal to p0 prime, which is what you have here, right? Because once you have used this delta function, ep and ep prime becomes equal. So what we get is 1 over 2 pi times integral dt, right? Because this is just 1. And so this is saying that the divergence that you are finding here, okay, it's indicating as if the probability is infinite, right? Now, is it sensible that the probability is infinite? Okay. The reason that it's sensible is because we expect that this chi particle will have a finite decay probability per unit time, right? Because if chi has a finite lifetime, right, that means it has a finite decay probability per unit time. So of course, if you wait for infinite time, then the probability that it will decay is infinite. Okay, now of course, probability cannot be infinite, right? It's bounded by 1. But this basically means that the probability becomes so large that this whole approximation breaks down. So this suggests that the correct thing to do, okay, is to not look at the probability itself, okay, but probability of decay per unit time. Okay. You divide this probability by this time interval. Okay. Or imagine that you are working with in a quantum field theory over a finite time interval. Okay. And then we calculate the ratio of the probability to the time interval. Okay. That will give a finite answer. Okay. Because that basically says that you just remove this delta of 0 from here, because you are integrating by, you are dividing by this integral, and you have to still keep this 1 over 2 pi. Okay, that because you are only dividing by this. So if you do that, okay, and if you call this transition probability per unit time as p dot, there you can get a finite result, right? Because you get the same integrals as before. Okay, I have not done anything here. This 2 pi to the 8 has become 2 pi to the 7 because of this 1 over 2 pi. I still have this delta 4 of qi minus p. Here I only have the delta cube of p minus p prime, because this delta 0 I replaced by this integral and divided by this. And this part again is the same as before. So this then is our expression for the rate of decay, or the decay probability per unit time. Are there questions? So this quantity is in fact finite. Okay, and you can calculate this, and we will try to simplify this in the next slide.
Sir, we are dividing 1 by 2 pi integral dt with p.
Yes, so you are dividing p by this integral dt.
Then we will get 2 pi whole power 9, not 7.
No, see, okay, this, there is a delta of p0 minus p0 prime here, right?
Yes.
Okay. So in this expression, delta of p0 minus p0 prime, I rewrite as 1 over 2 pi times integral dt.
Yes, sir.
Okay, so that 1 over 2 pi then becomes part of this expression, right?
Yes.
So that 1 over 2 pi combines with this 2 pi to the 8 to give you 2 pi to the 7.
Okay, sir. Okay. Okay.
And that integral dt that is left over, that's what we divide by.
Okay, sir. Okay. Okay, sir. Okay, fine.
Okay.
Fine. I got it.
Okay. Is there any other question? Okay, so let's proceed then. So this is the same expression. Okay, I have just taken the same expression and rewritten it again. Okay, but now you can simplify it, because first of all you can do the p prime integral easily, right? By setting p prime equal to p. So that gives you this. Okay, so let's see what I have done here. So I have just removed this and set p prime equal to p everywhere, removing the p prime integral. So this becomes 2ep, for example, instead of 2ep prime. And this m has now both arguments p, okay, instead of 1p and 1p prime. Okay. And now I'm going to use the fact that f of p is a shortly peaked function. Okay. so that we can basically set EP by EP equal to EK, or whenever there is a P, I can replace it by K, except of course in the product F tilde times F tilde star, because both are rapidly varying function. So I'll separate this out. Okay, I'll use the fact that integral dq p over 2p F tilde p times F tilde p star equal to 1. And then in the rest of the expression, whatever is left, I just substitute p by k, replace p by k. So that gives you, so there are 1 over 2 EP, 1 over 2 EP, one of the 2 EPs went here, right? The other one became 2 EK, so that's 1 over 2 EK. And then you have these integrals, okay? The Q integrals, then you have a 2 pi to the 4. Okay, why is it 2 pi to the 4? So what I have done here is I have just picked this minus 3 from here, combined this 2 pi to the 7 to make it 2 pi to the 4 delta 4 sum over qi minus k. Okay, I have replaced p by k. This now has become 2 pi to the minus 3m, and then the product of m and m star. Is this clear?
Sir, please explain why we are replacing p bar with k bar.
Okay, yeah, because f tilde, okay, I have chosen to be a sharply picked function around k, right?
Yes, sir. Yes, sir.
Okay, there's a width sigma, and eventually you want to take the sigma to 0 limit.
Yes, sir.
So in that limit, anything which is varying smoothly, you can just replace by k.
Yes, sir.
Okay? Except in this product, right? So that's why I have separately done this integral, written as a 1, and everywhere else I have replaced p by k.
Okay, sir.
Any other question? So this expression, okay, tells you, okay, that if we take this chi particle moving with momentum k, okay, then what is the probability that it will decay into a certain final state? Okay. Here I have taken all the final state particles to be phi, but of course this can be generalized, right? For example, as I said, muon decays into electrons and a pair of neutrinos, okay, and you can calculate using the appropriate theory of interaction of muons, okay, as to what will be the distribution, okay, of electrons and neutrinos that we'll have when the muon decays. And this is the kind of expression that one uses to get this. If you are interested in the total decay probability, okay, total rate of decay, then you just have to integrate over all the Q's, okay, over the full range. Of course, the full range is restricted by this delta function. Okay, and you have to divide by m factorial. Okay, as I have said, that if you just integrate each of these Qi's over the full range, then you will overcome, right? Because exchange of the two Q's, suppose Q1 is K1 and Q2 is K2, and Q1 is K2 and Q2 is K1, they describe the same final state configuration. So you shouldn't sum over them twice. So similarly, because there are m identical particles, if you are integrating over each Qi over the full range, then you have to divide by 1 over m factorial. Okay. More generally, whenever there is an overlapping range, okay, whenever the range of Qi and Qj overlap, you have to divide by appropriate symmetry factor. But this, of course, can be done, and you can calculate the probability, decay probability by doing this. Are there questions on this? Okay, so this is what I have said here. So let's do some simple calculation. Let's suppose that we start with n0 chi particles, and each of the chi particles moving with some momentum k. And then we want to know how many particles will remain at time t. So that is obtained by this solving this differential equation. dn dt should be equal to the minus of the decay probability per unit time times the number of particles that we have. Right? So this is the rate at which the n gets depleted, okay? Because this particle, chi particle, is going to decay into phi particles. So P dot, of course, is time independent, right? This is time transition invariant expression. So you can integrate this by thinking P dot as just a constant. So n is n0 e to the minus P dot t. And from here you can find the half-life, because half-life is when n over n0 is half. So half-life tau is obtained by solving this equation, e to the minus tau p dot equal to half, or tau equal to 1 over p dot log 2. Now, here you would notice that you have this 1 over 2 Ek factor inside p dot. Everything else, in fact, is k independent. It doesn't look like k independent, but it is k independent from the following considerations. That you see that these are all Lorentz invariant expressions, right? This is also Lorentz invariant. And the way we have defined M, that's also Lorentz invariant. Okay, this we can explicitly check because M is basically the amputated Green's function. Okay, with some 2 pi factors taken out. So this integral is fully Lorentz invariant. So if you make a Lorentz transformation of K, right, you can change this momentum K to any momentum that you like. Okay, in particular, you can go to the rest frame of the particle. So this part of the expression is not going to change. However, Ek is not Lorentz invariant, right? Ek is the energy of the particle. Okay, so clearly, if you change K, Ek is going to change. So what this is saying is that the half-life of a particle, of the chi particle, is proportional to Ek, where K is the momentum that the chi particle carries. So larger the momentum, the longer it lives. Now this may sound counterintuitive. How can the lifetime of a particle depend on its momentum? Okay. But it simply follows from time dilation, right? So even if you didn't know anything about all these calculations, right? If you just knew about special relativity, and if you knew, for example, that in the rest frame of the chi particle, it has certain lifetime, then you can consider a moving chi. In its rest frame, okay, its lifetime is fixed. But then by using the Lorentz transformation, you can ask how much time interval it will correspond to in the frame in which the chi particle is moving. And that's calculated by simple time dilation formula. And you will find exactly this result. Okay, the ratio that you will get is Ek over M. Okay. In the rest frame, the lifetime is, if the lifetime is some constant times M, then in the moving frame, the lifetime will be Ek times the same constant. Okay, are there questions? Okay, so if not, we'll move to the next topic. So this is as much as I'll say about scalar field theories. But all the ingredients of a quantum field theory are basically encoded in this discussion, right? So what we'll be doing next is we'll be to generalize this to other kinds of field theories, but all the general procedure will be identical. Okay, so in fact, I'm not going to go through the general procedure again, okay, but I'll just write down the final result, okay, by invoking whatever you have done with scalar field theories. So we'll start with something that you are familiar with, quantization of the electromagnetic field. In fact, today's lecture will not be on quantization. Today's lecture will be on some manipulations involving classical electromagnetic field. Because the way we'll proceed, okay, the strategy that we'll be following is that first we will try to manipulate the classical theory of electromagnetism and try to bring it to a form that is suitable for quantization and then quantize it. Okay? Because as we will see, in the original form, okay, it's not very suitable for quantization. Okay, you have to do, I mean, it doesn't satisfy the usual properties, but that allows you to quantize it immediately. Okay, so we'll start with a Maxwell action. I'm not sure if you are familiar with this covariant form of Maxwell's action, but I'll say what it does. So F mu nu here is the covariant Maxwell field strength. Okay, so F mu nu is del mu nu minus del nu mu. F upper mu nu is just the indices raised by the eta, okay, by the standard Lorentz invariant procedure, and mu here is a vector potential. So A0, for example, is minus phi. Okay, for phi is the electrostatic potential, okay, and AI, the spatial components, is the magnetic vector potential. Okay, that's the way we build the 4-vector mu. Now let's check that this action, okay, I have just proposed that this is the action. Okay, let's check that this action gives the correct equation of motion. And here you are talking about just free Maxwell's theory. Okay, no coupling to anything. Okay, eventually, of course, we'll want to couple it to other things. So let's check if this action reproduces correctly the equations of motion. Okay. So you take a variation, okay, arbitrary variation of the basic fields, which is mu. So that variation, so there is a minus 1/4 here, but the variation of these two, of course, gives the same answer because it's perfectly symmetric in these two f mu nus. So I'll vary only one of them and make it into half. So you get integral d4x f mu nu times del mu delta nu minus del nu delta mu. And now you notice that because this is antisymmetric under mu nu exchange, these two give actually the same result, right? Because this is the second term is just the first term with mu nu exchange and the minus sign. So the second term will give the same result as the first term because f mu nu is automatically antisymmetric under mu nu exchange. So that takes care of the other two also. Okay, it becomes minus integral d4x f mu nu times just the first term del mu delta nu. And now you do an integration by parts, throwing the boundary terms, throwing out the boundary terms, and we get this. And now we use the fact that delta nu, of course, is an arbitrary variation. So the equation of motion that we get is del mu f mu nu equal to 0. Okay, so that's the way we get the Maxwell's equation. Okay, so this is the covariant form of the Maxwell's equation. Okay. If you are not familiar with the covariant form, you can just write in components, and that will give the usual Maxwell's equation in terms of vector potential and electrostatic potential. Okay, are there questions on this? Okay. So now let's write down the Lagrangian. Okay, Lagrangian, of course, you just drop the time integral. Okay, from this, sorry, from this, the Lagrangian is minus 1/4 integral d q bar times f mu nu. Okay, that's what I've written here. And now I'm going to rewrite this in terms explicitly in terms of space and time coordinates separately. So mu can be either space coordinate or time coordinate. Nu can be either space coordinate or time coordinate. I'll denote the time coordinate by 0 and the space coordinates by I, where I or j can take values from 1 to 3. And the way I'm writing is, it is understood that repeated ij indices will be summed from 1 to 3 automatically. Just like repeated mu nu indices are summed from 1 to 4, sorry, 0 to 3. The repeated ij indices will be summed from 1 to 3. So first consider the case when mu is 0. Okay, if this is 0, then of course this is also 0. And if mu is 0, then we can see that nu cannot be also 0, but f00 is 0. Right? F00 is 0 by definition, it's antisymmetric. So if mu is 0, nu has to be I. So that gives you this term, f0i, f0i. Then you consider the case when mu is I. In that case, nu can be either 0 or j. Okay, so mu is I, nu equal to 0 gives you the second term. And then this is the final term, okay, when the mu is I and nu is j. Okay, so now these two terms are of course the same, right? Because of the antisymmetry, f0i is the same as fi0. So I write explicitly those two terms here. And the minus 1/4 has become half here, okay. The minus sign has gone, okay, let's see why. Because what I've done here is that I've lowered all the indices, right? When you lower all the indices, of course, I index lowering doesn't do anything because eta ij is delta ij. When you lower the 0 index, you get a minus sign. So that minus sign basically takes away the minus sign over here. So that's the reason why there is a minus sign here. And then because these two terms are identical, it's basically 2 times 1/4. So that gives you half. So this is the term that you get as the sum of these two. And then the second term I have kept as it is. Okay, minus 1/4, but I have just written both terms, both indices down, because lowering ij indices doesn't make any difference. Okay, because of this fact that eta ij is delta ij. So this is the form of the Lagrangian that we'll be working with. Okay, are there questions? Okay, so let me proceed. So here is the Lagrangian again. Now let's try to see. Okay, to quantize normally you have to go to Hamiltonian of the system, right? And then you apply the Poisson brackets. You write down the Poisson bracket and then you make them into canonical, the commutator bracket. Okay. So let's try to do that. Okay, but if you want to go to the Hamiltonian formulation, we have to define the momentum first, right? The conjugate momentum. Okay. So pi I will be delta L delta AI dot, pi 0 will be delta L delta A0 dot. This has no problem, right? There is the AI dot term here. But you see that there is no term here in the Lagrangian which has A0 dot, right? No term involving time derivative of A0. Because Fij of course has only edges, right? It's del I Aj minus del J I. A0 comes here, but A0 comes only with a space derivative, no time derivative. And that has to do with the fact that F00 is identically 0, right? F00, which would have gotten given some A0 dot term, is identically 0 because it's antisymmetrist. So this is telling us that pi 0 actually vanishes. And if pi 0 vanishes, that means it's a constant system. The momentum are not independent variables. Okay? The momentum conjugate to A0 is actually 0. Now, if you remember, we discussed long time ago that if you have a constant system, we can use Dirac's formalism for quantizing constant system. Here, in fact, things are a little more complicated. Earlier, when you are dealing with the Schrodinger system, Schrodinger field theory, we showed how to use Dirac's formalism. But there, all the constants are second class, so it was easy to eliminate them. Here, it turns out that some of the constants will be first class. So you can still certainly use Dirac's formalism, but it requires then understanding Dirac's formalism better, right? It's not just enough to understand how to deal with second class constants. So what we will do is to use a slightly different procedure. Okay, the final result, of course, will be the same as what you would get if we apply Dirac's formalism. And that this different approach that I'll be using is based on what is called the Routhian.
Sir?
Yes, go ahead, please.
Excuse me. Please explain why by this pi naught 0, because if you look at the L, it depending on A naught.
Yeah, A naught. But this is this derivative with respect to A naught dot, right?
Yes, yes, sir.
So this is time derivative.
Yes, there is no term of time derivative of A naught, right?
Exactly.
Right.
Yeah, that's why pi naught is 0.
Yes, sir. Thank you, sir.
Okay. Okay, are there questions? Okay, so this Routhian is a concept from classical mechanics. Okay, it's the generalization of Lagrangian and Hamiltonian. Okay. You might have already encountered this when studying classical mechanics, but if not, I'll try to briefly outline what the Routhian is about. Okay, it's basically something in between the Hamiltonian and the Lagrangian. Okay. So let's forget about field theory for now. Okay. Let's just consider a classical dynamical system. Okay. So classical dynamical system whose coordinates variables I'll divide into two parts. Okay. One set I'll denote by QA, okay, with A running from 1 to M, and another set I'll denote by Q alpha, with alpha running from M plus 1 to M plus N. Okay. And this division is completely arbitrary. It's up to us to divide, okay, the coordinates, okay, the coordinate variables into these two sets. Okay. And what I'm going to describe, okay, will work for arbitrary choice of coordinates like this. Okay. But of course, when you apply it, we'll apply it according to our convenience. Okay, so this is what I've said. How we divide the coordinate variables into these two sets is up to us. Now, to begin with, L is in general a function of Q dot. So QA dot as well as Q alpha dot. Right? That's the way we write the Lagrangian of a classical dynamical system. That is a function of the coordinates and the velocities. Now, when you go to the Hamiltonian formulation, right, you define conjugate momentum P as del L del Q dot. When you go to Routhian, what I'm going to do is that we'll introduce conjugate momenta but only for a subset of the variables, the subset of the variables which carry the level A, but not for the subset of the variables which carry the level alpha. So I introduce PA as del L del QA dot, and I define the Routhian, which is now expressed as a function of QA PA, and of course we have not introduced any P alpha, so Q alpha dot. So this is defined as sum over A equal to 1 to M PA QA dot minus L. So it's as if we are going to the Hamiltonian formulation, but in that, on the way, we have forgotten about the Q alpha variables. Okay, and you have gone to the Hamiltonian formulation only with a subset of the variables, which are labeled from by A from 1 to M. Okay, is this definition clear? Okay, so I'll leave it as an exercise for you to check. Okay, so the Euler-Lagrange equations, right? So what are the Euler-Lagrange equations? Euler-Lagrange equations are ddt of del L del Q dot equal to del L del Q, right? For all Q's, right? That's the starting point, right, of the Lagrangian formulation. So what I'll leave it as to you as an exercise is to check that the original Euler-Lagrange equations, okay, which are ddt of del L del QA dot minus del L del QA equal to 0, and ddt of del L del Q alpha dot minus del L del Q alpha equal to 0. Those Euler-Lagrange equations can be rewritten now in this fashion. Okay, these carry exactly the same information as the original Euler-Lagrange equations. So these take the form dqa dt equal to del R del PA, dpa dt equal to minus del R del QA. You might recognize this as the Hamiltonian equations. Instead of Hamiltonian, here you have the Routhian. But of course, for the A variables, for the QA variables, the Routhian is like the Hamiltonian. Okay. On the other hand, for the Q alphas, the equations, Routhian depends on Q and Q dot, and the equations take the form of the Euler-Lagrange equation, ddt of del R del Q alpha dot minus del R del Q alpha equal to 0. So in a sense, Routhian is playing the role of the Hamiltonian as far as the variables QA, PA are concerned, and it's playing the role of the Lagrangian as far as the variables Q alpha dot are concerned. But this is just an mathematical identity that these equations one can show are equivalent to the original Lagrangian equations, the Euler-Lagrange equations. And the procedure is basically the same that you use to show that the Hamilton's equations are equivalent to the Euler-Lagrange equations. Okay, are there any questions? Okay. So here I have again rewritten all the definitions, right? PA is del L del QA dot, Routhian is defined here, okay, as if it's the Hamiltonian, but only for the variables QA. Okay. And here are the equations, right? It satisfies Hamiltonian-like equations for the variables QA, PA, and Lagrangian-like equations for the variables Q alpha dot. So what you are going to do now is to apply this Routhian formalism to Maxwell's theory. We are still doing all classical physics, right? We are not in fact going to do quantum mechanics today. Okay, just analyzing the classical dynamical system. Okay? Only after you have brought it into a form, okay, which is suitable for quantization, that will quantize it. Okay, so when you apply it to Maxwell's theory, we are going to treat the AIs as the QAs. So that means for these, we'll use Hamiltonian-like formulation, and the A0s as the Q alphas. That means the A0 will treat as if it's like a Lagrangian in the Lagrangian formulation. And you can immediately see the advantage that you don't have to worry about pi 0. Right? Because if you are trying to treat A0 in the Hamiltonian formulation, then you run into this problem that pi 0 is 0. Okay? But let's not do that. We'll just simply treat this in the Lagrangian formulation. Okay, and see what we get. Are there questions? Okay. So let me proceed. So here is the Lagrangian. So let's define pi I. So pi I is the variation delta L delta EI dot. Okay, so this in fact we already have introduced earlier, and you can now calculate what it is. Okay. EI dot basically comes from here. Okay, and of course here. So when you take the derivative, right, you can either take the derivative of this or the derivative of this, they give the same result, and you get del 0 EI minus del I A0. And this you may recognize as the negative of the electric field, right, in the standard sense. Okay, because this is like grad phi, A0 is minus phi, and this is dA dt. Okay, that's minus the electric field, but we will not really need the interpretation as electric field very much. So using this, we can construct the Routhian now. So it's integral dq bar pi I EI dot minus L. Okay, so I'll leave it as an exercise. This is some little manipulations you have to do. Okay, let me just say how to do this. Okay. So see, this is already in the form of pi I, right? So the Lagrangian has a half pi I in this, minus 1/4 Fij. So that's 1 minute. Okay, so what we do is that AI dot, right? We have to express AI dot in terms of pi I, right? Because for AI dot we are treating in the Hamiltonian formulation. So using this AI dot, I write as pi I plus del I A naught. Okay. I think I am getting some echo. Can you hear me still?
Yes, sir.
Yeah.
No, I think there is some problem here. I know what is the problem. That the audio has come on. Okay. 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 In case there is a disturbance, please let me know. Okay. So what I did, AI dot. Okay, I replace in terms of pi I. Okay, using this. So AI dot is pi I plus del I A naught. So here we get a pi I square. Okay, and here you have a half pi I square. So that gives you, the difference gives you half pi I. Now when you subtract L, so but there will be leftover term, which is del I A naught times pi I. That I do an integration by parts to write as minus A0 times del I pi I. And then this term, okay, minus half 1/4 Fij becomes plus 1/4 Fij because it's minus L.
Sir,
Yes, go ahead, please.
please explain from this line in the Maxwell's theory we shall treat it, because I'm confusing Fij product. Fijs are nothing but I think the components of electric fields. These are
No, these are components of magnetic field. In fact, Fij is del I Aj minus del J Ai, right? That's like curl of A.
yes.
So these are like magnetic fields.
Okay.
So these don't have any time derivative.
But if we change our convention as a time component, if we drop down to time component, it is taken place. And if space components are, if we down them, if we get negative, then Fij, I think they are electric fields in that sense.
Yeah, but we don't, I mean, normally what we do is that we think of the electric field, okay, as, so let's look at the expression for the electric field, right? Up to sines, right? There's a gradient of phi, okay, the electrostatic part, and then there's a dA dt, right? The
Yes.
derivative of the vector potential. That is this one, right? Because A0 is like phi. So this gives a gradient of phi, and this gives the time derivative of A.
Yes, this time derivative of E. Yes.
Right? So this part is the electric field.
Okay.
Okay. This part Fij is like del I Aj minus del J Ai, right?
Yes, sir.
So del I Aj minus del J Ai is like curl of A, right?
Yes, sir.
And curl of A is normally we think of this as a magnetic field.
Yes, sir. Yes.
Right? So that's why this is more like a magnetic field.
Okay, sir.
In fact, this is what I have written here.
Okay.
So basically this 1/4 Fij we can write as half Bi. This I will leave as an exercise to check.
Okay.
So where Bi is given here.
Okay, sir.
Okay, it's epsilon ijk del j ak. So this is basically curl of A.
Yes, that is the definition of curl. This is right.
Yeah, this is basically the definition of curl, right?
Yes.
Okay, is this point clear?
Yes, sir. Yes, sir.
Okay. Okay. So just work this out carefully and you will find this is a straightforward exercise, that the Routhian in this case is given by this sum. That there's a pi I, there is a bi, and then there's a minus a0 del I pi I. So now we can write down the equation of motion for all the fields. So the equation of motion for A0, this of course has to be done in the Lagrangian formulation, in Euler-Lagrange equation. So del T of delta R delta A naught dot is minus delta R delta A naught is equal to 0. This is still 0, right? Because Routhian doesn't depend on A naught dot. So this variation just gives you del I pi I equal to 0. Which in terms, if you think of pi I as the electric field, then this just tells us the divergence of E is 0. Which of course you know is one of the Maxwell's equations because there's a source here, right? We have not put a charge source. And then the equations of AI and pi I, we can get, okay, so del AI del T should be delta R delta pi I. This is like the Hamilton's equation.
Sir?
Yes, go ahead please.
So in the equation of motion of A naught, there should be total derivative of time with respect to time or partial derivative.
Okay, total, this is actually normally we write as total derivative, but the point is because A0 also depends on R, right? This derivative has to be taken at fixed R. Okay, that's why I have written as a partial derivative.
Okay.
That point clear, right? Because in fact, this is true also in scalar field theories, right? I have been writing del T square phi, right? And the reason is that because phi depends on T as well as R, okay? And to indicate that the derivative with respect to time when you take, right? You are doing it at fixed R. Okay, that's why this partial derivative. Okay. Are there other questions? Okay. So this one del AI del T, right, should be this is the we are now using like Hamilton's equation, right? So d dt of a coordinate is the variation of the Hamilton with respect to the momentum, right? So delta R delta pi I, and delta R delta pi I you can calculate from here because there is a pi I coming from here, and here we just do an integration by parts, right? So it's pi I times del I A0, so that gives you a del I A0 factor. Okay, so that's delta R delta pi I. And del pi I del T is equal to minus delta R delta AI. Here you have to do a little more work. So AI dependence here is actually inside B, right? Because B has a curl of A. So you have to do a little more work to calculate this variation. But I'll leave it as an exercise to check that you get basically as minus epsilon ijk del j bk. And you can convince yourself that these are exactly the Maxwell's equations, that the free Maxwell's equation that we are familiar with. Okay, that once you understand, once you interpret pi I as the electric field, okay, these are in fact free Maxwell's equation. Okay, are there questions? Okay, so these two equations are in fact nice. Okay, if somebody gives you A0, okay, these two equations, the first equation tells us how to evolve A as a function of time, and how to involve, second equation tells us how to evolve for pi I as a function of time. Okay. So if somebody gives you some initial AI and pi I, okay, you can use this to evolve AI and pi I in time. Okay, suppose give you some initial configuration AI of 0R and pi I of 0R. Then these equations can be used to solve for AI of TR and pi I of TR. Okay, a set of coupled equations. However, the problem comes as far as the A0 is concerned. First of all, you see that the A0 equation gives a constraint involving pi I. This, in fact, is not a very serious problem. And the reason is that you can see that if this equation, for example, right, what does it tell us? If you take the divergence of this, okay, you have del pi I del T equal to 0. Suppose you take the divergence of this, right, del I of this. Del I, of course, commutes to del T, so that goes inside. So it tells us that del T of the divergence of pi is divergence of this, but that is actually 0. because if you take epsilon ijk, del I del j bk, right? Because del I del j is symmetric under ij exchange, and epsilon ijk is totally antisymmetric. That's identically 0, which of course you are familiar with. It's just the statement that the divergence of a curl is 0. So as a consequence of this equation, the del I pi I, the time variation of del I pi I is identically 0. So even though this equation looks like an equation that has to be imposed at every point, every instant of time, it's in fact enough to impose it at the initial condition. So you choose your initial ai and pi I such that pi I satisfies this condition at the initial time, say t equal to t naught. Then you don't have to worry about this constant anymore. Okay, you evolve ai and pi I by these two equations, and del I pi I will automatically remain 0 at all future time. Okay, just as a consequence of this equation. Is this clear? Any question? Okay. However, the problem comes because you see that there is no equation that gives the time evolution of A0. Right? All of these simply involve AI and pi I, right? So these two equations, for example, tells you that for a given A0, it will tell you how to evolve, time evolve AI and pi I, but nothing tells us how to time evolve A0. In fact, if you look at these equations, then A0 at a given time can be taken to anything that you like. Okay, irrespective of what the initial condition on A0 was, A0 at any later time can be taken to be anything that you like. Okay, because nothing tells you how A0 evolves as a function of time. Are there questions?
So in Lagrangian formalism, as such, gauge does not play a role.
Well, it is going to play a role. So far, you have not fixed any gauge.
Yeah, I mean, the Lagrangian itself is unaware of whatever gauge choice we have.
Yeah, exactly. So you have not made any gauge choice at the level of the Lagrangian.
I mean, even if we had started with some gauge choice, would it matter coming to this point?
Well, if you had, I mean, we have assumed that the AMUs can be varied independently, right? The equations of motion that you have derived, right? You have derived by varying AMUs independently.
Yeah.
Right. So if you had put a gauge choice from the beginning, then you cannot vary AMU independently, right?
But that is how it should be, right? Because a gauge choice is sort of a constraint.
Well, it's not exactly a constant, but you can think of it as a constant, but it's something that you have to impose by hand.
And that is at the end.
That we'll do now.
Okay.
Okay. At the level of the Lagrangian, okay, you can proceed without fixing any gauge. Okay. But this feature is precisely reflecting that fact. The fact that the time evolution of A0 is not determined is precisely because of the gauge freedom. Right? And this is what we are going to discuss now. Is this okay? So at the level, so far you have not said anything about which gauge you are working in, right? In fact, we have not fixed any gauge so far. Okay, any other question? Okay. So this is the point about gauge freedom. Basically, the inability to determine A0, right? This arises from the gauge invariance of the theory. So what is gauge invariance? Gauge invariance is the statement that if mu solves classical equations of motion, then mu plus del mu lambda for any function lambda also satisfies classical equations of motion. And the reason is simple, okay, that f mu nu is not affected by this change, right? Because f mu nu has del mu nu minus del nu mu, right? So this shift will just cancel out in the expression for the f mu, right? You will get del nu lambda minus del mu lambda, which is just 0. And if f mu nu doesn't depend on lambda, then that basically says that the equations of motion, let's look at the equation of motion, which was written in terms of f mu nu. here, whichever lambda you choose, right, the new configuration is going to continue satisfy equations of motion because F mu nu doesn't change, okay, independent of what lambda you choose. And it is because of this, okay, that even if you start from a given configuration, that the time evolution is not unique. Because given any solution, you can always add del mu lambda, okay, to the to mu. Okay. So suppose you are given some solution mu, we add a del mu lambda, okay, for arbitrary function lambda. Okay. And if you have fixed your initial condition on a0, for example, right, then let's choose lambda such that time derivative of lambda is 0 initially. Okay, so the a0 doesn't change. You are not changing the initial condition. Okay. But we can choose it to be arbitrarily later, right? At a later time, okay, lambda can be anything. Okay. So even if the initial condition remains fixed, okay, we can change mu at a later time, okay, simply by choosing lambda appropriately. Okay. So it's not surprising that the equations that we got, okay, does not determine the time evolution of a0. Okay, because it is not supposed to determine the time evolution of a0. Okay, otherwise, that freedom will be lost, right? And we know that we have this freedom of changing mu by adding any del mu lambda. But of course, the F mu nu, okay, as well as all the other things, okay, E and B are of course part of F mu nu. The Lagrangian, for example, these are all invariant under the gauge transformation. Okay. So because we cannot determine the time evolution of mu, okay, we do the next best thing that we can do, okay, that we simply declare that mu and mu plus del mu lambda describe equivalent field configurations. Okay. Which means that all physical quantities, okay, should not depend on whether you are using mu or mu plus del mu lambda. Okay. If you change mu to mu plus del mu lambda, all physical quantities must remain the same. So the physical quantities means, okay, for example, F mu nu, right? F mu nu will be a physical quantity. So this is the way you define physical quantities. Okay? Physical quantities in electromagnetism are those quantities, okay, which do not change under mu going to mu plus del mu lambda. Okay? So this is another way of saying this. The time evolution of mu is not determined, but the undetermined part is not physically relevant. Okay? Because all physical quantities are unchanged under this transformation. Is this point clear? Okay. So basically, because of this gauge freedom, right, we could proceed in principle, okay, without fixing a gauge, because there will be an ambiguity in determining mu, but who cares about mu? Because all physical quantities are determined in terms of things which are gauge invariant. Okay. Nevertheless, it turns out that to do perturbation theory, okay, and which is what we want to do, okay, we need to fix a gauge. Okay. Because otherwise, for example, we will find that the propagator, if we try to use this full Maxwell's equation, Maxwell's theory, and try to calculate the propagator for the mu field, okay, you will get infinite answer. Okay. So if you want to do perturbation theory, we have to fix a gauge. Okay. And we will do this. That means we solve this ambiguity by fixing a gauge, okay, which means we pick one representative configurations among all the gauge equivalent ones. Right? We are saying that there are many configurations which are all gauge equivalent because they differ by del mu lambda. Okay. But now we say that, okay, that may be so, but let's just pick one of them, okay, and work with that. Okay. Because since we know that everything is independent of the choice of gauge anyway, okay, it doesn't matter if we pick any one of them, right? And we choose one at our convenience. Okay. Are there questions? Okay. So I'll give a particular choice of gauge that we'll be using. Okay. But of course, there are many other choices possible. Okay. And in fact, you will probably encounter other choices of gauge later, okay, which are more covariant, which are more manifestly Lorentz covariant. Okay. But what we'll use is called the Coulomb gauge, okay, where we put the divergence of A equal to 0. Okay. So first, you have to check if this is always possible, right? That is it always possible to choose divergence of A equal to 0? Now, what does that mean? That means the following, that suppose you are given a configuration for the divergence of A is not equal to 0, then can you find a lambda so that the new A that we get, namely, sorry, this is wrong. This should be divergence of lambda, gradient of lambda. Okay, not divergence of A plus lambda. Okay? This A plus gradient of lambda. Okay? So A plus gradient of lambda will be the new spatial A, right? New spatial components of A. Okay? So you have to make sure that it's possible to choose a lambda in such a way that the divergence of A plus gradient of lambda is 0. So that, of course, is an equation that can be easily solved, because once you write this as the gradient of lambda, okay, the equation takes the form gradient square of lambda minus equal to minus divergence of A. Okay, is this clear what we are doing here? So basically, you want to make sure that given any A which doesn't satisfy Coulomb gauge condition, okay, it is possible to gauge transform it to a configuration which does solve Coulomb gauge condition, right? Which means the divergence of A plus gradient of lambda must be 0. So this gives an equation for lambda. And now the point is that because it's this ordinary Laplacian in 3 dimensions, okay, this equation can always be solved by the 3-dimensional Green's function. So this curly G here is just a 3-dimensional Green's function. So this equation has a solution where lambda is given by this. Okay, it's integral d cube r prime g r r prime, and then whatever is on the source on the right hand side. Sorry, d cube r prime has come twice, so it's just one integral here. Okay, so are there questions? Okay, so let's now see how this solves our problem. Okay, because our problem was that A0, the time evolution of A0 was not given, right? So now let's say after you have imposed this Coulomb gauge condition, how does it fix the time evolution condition for A0? So for this, we look at the one of the equations that we had derived earlier. Okay, that's this one. This one. Okay, let's look at this equation. That is del AI del t equal to pi I plus del I A0. Okay. So that's this equation I've written. Now take a divergence on both sides. So the left hand side gives you divergence of the time derivative of divergence of A, right? Because of course the space and time derivatives commute. Okay, so left hand side is then is 0. Okay, because this time derivative of divergence of A. On the right hand side, you have divergence of pi, del I pi I, and then this gives you the 3-dimensional Laplacian acting on A0. This, of course, is 0 by the constant equation. So we get that the Laplacian, the 3-dimensional Laplacian acting on A0 is 0. So in the Coulomb gauge, that means that the equation for A0 is just Laplacian on A0 equal to 0. And now if we use the boundary condition that A0 falls up to 0 at large R, then that gives a solution A0 equal to 0, right? Because again, by the same thing, instead of lambda, now you have A0 on this side and 0 on the other side, right? So the solution is given like this, and if the source is 0, you get A0 is 0. So in the Coulomb gauge, then the A0 is 0 at all times. Now you could have said that okay, you might as well have chosen the gauge condition as A0 equal to 0, right? Why go through Coulomb gauge? Okay, but we'll see that this will make that these two statements are not the same when there are source terms, right? And eventually you have to deal with source terms in the equations of motion. Okay, so Coulomb gauge, the divergence of A equal to 0 and A0 equal to 0 are not always going to be the same. Okay, but in this case, indeed, we could have said that we choose the gauge condition A0 equal to 0. Okay, instead of saying that we are choosing Coulomb gauge condition. Okay, are there questions? Okay, so let's see what we have gotten in this gauge. Okay, so in this gauge, the non-trivial equations of motion, one can write as del ai del t equal to del r del pi I, but now this quantity is just pi I. Let's look at the original equation. So basically what we are doing here is that I'm just setting a0 equal to 0. Okay. I'm setting a0 equal to 0 here, and I'll also set a0 equal to 0 in the expression for the Routhian. Okay. So this is one of the equations. Then del pi I del t is equal to minus del r del I. Here nothing has changed. Okay, this remains the same form. It retains the same form. Okay. In the expression for Routhian, I have dropped the last term, okay, the a0 del I pi I term. Okay. And now we have two external conditions. Okay, we can call it constraints or you can call it conditions that you have to impose. This one came from the constraint, the a0 equation. Okay, so that you have to impose. Okay. And now this one is a Coulomb gauge condition that also you have to impose. So to summarize, the dynamical system that you have arrived at, okay, is this Routhian, okay, which now basically acts as a Hamiltonian for the fields ai and pi I. Okay, because these equations are exactly like the Hamilton's equation, okay, with the Routhian regarded as the Hamiltonian. But on top of this, you have these two conditions that you have to impose externally. These do not follow from the equations that you have already derived here. Okay. One is the divergence of a equal to 0. The other one is divergence of pi equal to 0. As we said, this one you have to impose only once, okay, because once you impose this, it remains. So we'll see later about this one.
So didn't we just make a gauge choice inside the Routhian?
Inside the Routhian.
Yeah, I mean, that's what I was saying, that whether we could do that at the level of Lagrangian or something.
Okay, if you do it at the level of the Lagrangian from the beginning, okay,
yeah,
then what you have to do is that sometimes you may miss the equations, right? That imagine that you had said a0 equal to 0 from the beginning.
Yeah.
Okay. Then this constraint that del I pi I equal to 0, you will miss. Right? Let's go back to Lagrangian here. Okay. So here is a Lagrangian, right? Suppose you said a0 equal to 0. So this will give you del 0 ai square minus 1/4 Fij Fij. You can derive the equation of motion from here. Okay. You will get these two equations will come out, not these two equations, the non-trivial equations will come out correctly. Okay. So for example, these two equations, the analog of these two equations will come out correctly. But what you will miss is what you get by taking the variation with respect to a0. Okay, because if you have already said a0 equal to 0 from the beginning, right, then there is no a0 equation anymore.
Yeah, but I mean, that is a problem in the sense that from Euler-Lagrange equations, we might not be able to get all the equations.
Yes.
But we already knew, gauge choice, gauge freedom only comes when you already know the equations of motion.
Or the Lagrangian. It's a symmetry of the Lagrangian also, right? Yeah, because f mu nu, see, look at Lagrangian. It's f, the action is f mu nu f mu nu, right? So at this level itself, you can see gauge invariance. Right? If you change a mu to a mu plus del mu lambda, nothing changes.
Is this true in general?
Yeah, this is true in general, right? Sometimes it may happen that it changes by total derivative, but in most applications, the action or the Lagrangian is gauge invariant.
Okay.
Okay. So there, if you naively decide that, okay, we'll fix a gauge from the beginning and set a0 equal to 0, okay, you will get most of the equations correct, okay, except that the sum of the variables that you have actually fixed, okay, their equations will be lost. So that's why one has to be careful, okay, to make sure that we are not losing any equation, right? Because now these equations, for example, right, that once I have said that you have the Routhian, and these are the equations that extra conditions that you have to impose, then you have not lost any equations, right? This you can easily check that these two conditions together with the Routhian gives all the equations that we had to begin with.
But are we sure that when we move ahead, and I don't know how we'll quantize, but when we quantize, we'll not miss out anything then?
Well, so far you have not missed out anything, right? As long as the same classical dynamical system as the original system, right?
Yeah.
We go ahead and quantize it. Right? That's the definition of the quantum theory.
We still have to take into account these constraints.
Yeah, we will. We'll see that there's a, once you go to the momentum space, these constants will just neatly separate out from the actual physical degrees of freedom. Okay? Right
Okay.
now we still have these constraints, okay? But let's note that these constraints you have to impose only once initially, right? Because look at the, okay, this you have already seen, del I pi I equal to 0, right? The time derivative of this constant is automatically satisfied, right? Because del I, the time derivative of this, okay, we saw is 0. Okay, I think that's the consequence of this one, right? If you take del I of this, it's identically 0. This one also you can check that the time derivative of this is 0, because if you take the del t of this, right, that's del I del ti. Okay, now del ti is pi I, so you get del I pi I, but del I pi I of course you have set equal to 0. So this is showing that indeed you have to impose these conditions, but it's not that you have to impose these conditions at every instant of time. It only says that the initial condition, okay, has to be restricted so that these two conditions are satisfied. Once you start with the initial condition that satisfies these two conditions, then you can forget about those conditions, okay, and just evolve the system just by thinking of this Routhian as a Hamiltonian. Pi i's and ai's are the conjugate variables of this Hamiltonian system, and you just write down Hamilton's equations, which are these two.
And in contrast, instead of fixing the Coulomb gauge, if we would have fixed the Lorentz gauge, we would have gotten another equation for del dot, A0 dot.
Yes, you would.
But and a lesser constraint like this one.
It will be different kind of equations. You will still get constants, okay, but it will be, see, this constant will always be there, right?
Yeah, yeah.
This one will be different in that case.
Yeah.
So in different gauges, you will have different procedures, right? The canonical formulation that we are using, that this using this Hamiltonian or the Routhian, here the Coulomb gauge is the most convenient choice.
Okay. Like later on, can we switch the gauge?
Well, I'll not switch the gauge, but I think in QFT2, you will probably use more convenient, more Lorentz invariant gauges, right? Like Lorentz gauge, as you said.
I mean, in the middle of solving, we cannot do that, right?
No, in the middle of solving, you cannot do that.
Yeah. Okay.
The final results, of course, will be gauge invariant. This you should be able to check that the final results are gauge invariant. But in the middle of solving, you cannot switch the gauge. Okay, so the point is that this will be our starting point for the next lecture. Okay, that we will start with this Routhian treated as Hamiltonian, okay, with these conditions. Okay, but as I said, these conditions have to be imposed only at the initial condition, as initial condition, but time evolution will be automatic. Okay, and then we'll see how to quantize it. Okay. But maybe before I finish, let me just say one thing, right? This is in keeping in mind the generalization, okay? Because ultimately you want to also couple it to sources, right? Like Dirac field, for example. Okay? That whatever we did, okay, goes through without much change, even if you have source term in the Maxwell's theory. Okay, that because in this presence of the source term, the Maxwell's equation has this structure, right? Del mu f mu equal to minus j nu, where j nu is automatically conserved. Okay, it's in fact it's a consequence of if you apply del nu on this side, right? The left hand side vanishes, so it better be that right hand side also vanishes. Okay, so j nu is a conserved current. Okay, we'll see that in the particular application that will be making, j nu will be coming from the Dirac fields. But at the level of the Lagrangian, we can achieve it by adding this term in the Lagrangian. This you can easily check. And if you add this in the Lagrangian, the corresponding Routhian, because Routhian has a minus L, okay, Routhian will get a term like this. So this gives us a few changes. For example, the A0 equation of motion will become now del I pi I plus J0 equal to 0. Okay, this is in fact the condition that the divergence of E is is rho, right? The charge density. J0 in fact is the charge density. So this is the analog of divergence of E equal to rho. Okay. So we fix the Coulomb gauge as before. Okay, divergence of A equal to 0, nothing changes. So this condition we still impose. Okay. But you can show that now because of this extra term J0 here, right? Remember how the A equation came? Okay. So here, okay, del I pi I is no longer 0, right? But del I pi I is minus J0. Okay. So you get del square A0 equal to J0. Okay, not 0. Okay, so you get del square A0 equal to J0. So A0 now is no longer 0. So this is what I had said earlier, that in the presence of source, Coulomb gauge is not the same as this temporal gauge where you said A0 equal to 0. Okay. So now A0 is given by this Green's function integral of J0. And using this, we can eliminate A0 and you can write the extra term that we have in R as this double integral. Okay, notice that this is still local in time, right? Because it involves product of currents at the same time, but it involves two space integrals. And the external constraints now are these, right? So basically what in the presence of the source, for all that will happen is that Routhian will get an extra term like this. Okay, otherwise so it will be this plus that extra term, okay, which is here. And then the constraints will change to del I pi I equal to minus J0 and del I AI equal to 0. And again, you can check that these constraints have to be imposed only at the initial time. Once you impose it at initial time, it will remain valid at all later times. Okay, so I think I'll stop here and we'll continue next time. So are there questions?
So, I mean, if there is a source,
Yes.
I mean, I'm thinking about quantizing electromagnetic field. So, if there is a source, how are we going to quantize that? I mean,
Yeah, we'll of course
source can itself. I mean, source can itself be coming from some quantum field.
Yes, indeed. It will. I mean, a J0, for example, will be like psi bar gamma mu psi. Okay, where psi is the Dirac field.
I mean, are we quantizing? Let's say we are talking about electromagnetic field interacting with electrons.
Yes.
So, are we quantizing both the electromagnetic field and the electric and electrons simultaneously, or we are quantizing electrons first and then electromagnetic field?
No, we have to do simultaneously.
Yeah. Okay.
Yeah. See, right now I'm doing classical analysis, right? So J0 is like a classical current. But when you quantize it eventually, right, I'll express, right, J0 in terms of the psi bar gamma mu psi, for example. Okay. And then you have to quantize the psi and electromagnetic field simultaneously. Yeah, it doesn't make sense to quantize electromagnetic field where the source is classical or vice versa.
Yeah.
Right? Because once the source becomes quantum, the electromagnetic field automatically becomes quantum, right? And vice versa. So you have to quantize them simultaneously.
But this thing is a coupling, right? Like it's only in the interaction theory. The free
Yes.
theory, we can quantize all fields separately.
Yes. Free theory, of course, one theory doesn't know about the other, right?
Yeah.
So you can do things separately. But once you have this coupling term, right, it doesn't make sense to quantize one part and not the other part.
Yeah, but for the sake of perturbation theory, we can sort of say something like there are independent creation annihilation operators.
Yes, so there will be independent in states for the electron and the photon.
Yeah.
And independent out states, certainly.
Yeah, that even this statement is quite specific to perturbation theory only, right?
Yes.
We cannot in general say that there is a field operator that creates electron or something.
Yeah, in general, no, right? I mean, I mean, this again you will learn probably in the next course or the particle physics, that in theory of strong interactions, for example, the quarks are the fundamental degrees of freedom, but there is no in-state in-state which is a quark or an out-state which is a quark, right? Because they don't exist as physical states. So in
That is
general, it is
because,
true that given a field, there may not be any in-state, there may not be a particle associated with that field.
and that is because of strong coupling.
Yeah, that's because of strong coupling. Right? The
Okay.
quarks are what are called confined, so they exist only as bound states. Okay, like protons and neutrons.
Yeah. I had a different question. Yeah.
Okay.
Yeah. In what we are doing regarding separating, like reorganizing our diagrams as one PI diagrams or amputated Green function, that
Yes.
is quite straightforward in something like a 5-4 theory. Although I think you were saying that this can be in general done for any theory.
Yeah, that can be done for any theory because that's diagrammatics, right?
Yeah, but even in diagrammatic sense, let's say the optional set that you gave in something like a phi square del grad phi whole square
Yes.
perturbation. I imagine, I mean, at least the way I was working through it, I encountered that not all edges are equivalent.
Yes, except that I mean the best way to do this is to make all of them equivalent by symmetrizing.
Symmetrizing the diagrams, not a single diagram. Like,
No, symmetrizing the well, you can do it if you want to do symmetrizing diagrams. It's complicated, right? But a single diagram you can symmetrize by saying that the vortex has sum of many terms. See, the Feynman rule for a given vortex, right?
yeah.
Need not have only one term, right?
Okay.
See,
I'm not sure.
okay, take 4.5 coupling, right? I know what problem you are talking about. This you are talking about the phi square grad phi whole square coupling, right?
Yeah.
Okay, so 4 phi's meet at a point, right? That's the coupling. Okay,
Yeah.
let's call the momentum P1, P2, P3, P4.
Yeah, and right now I am imagining that two of them are some other lines and two of the lines are the normal ones, the corresponding
But
to.
let's think of all the lines as phi. Okay.
Okay.
So in your way of doing it, it will have two of the lines will be special because you'll have something like P1 dot P2 coming out of this vortex, and no P3 dot P4, right? But
Yeah,
I'll write it as P1 dot P2 plus P1 dot P3 plus P1 dot P4 plus P2 dot P3 plus P2 dot P4 plus P3 dot P4 with an
that is
aggregation factor.
that is the sum of many diagrams.
No, that is some in my convention it will be sum of only one diagram. One diagram will contain all of it.
Yeah.
Right? I just define the vortex that way. See, in momentum space, right? You write, I mean, you can always symmetrize, right?
Yeah, we have to because we have to consider all diagrams. So all symmetric combinations will indeed come in.
Yeah. What I'm saying, if you try to think of this as sum of many diagrams, right? Then you will run into this confusion that you just mentioned.
Yeah, I get it.
Okay? But if you think of this as just as representing one diagram, right? One single vortex. You're thinking of there being many kinds of 4-point vortex, right?
Yeah.
I'm thinking of there being only one kind of 4-point vortex, but that has many terms in this expression.
I see, yeah.
Okay. Then there's a confusion. Then it's completely symmetric in the external legs.
Yeah.
For simple diagrams, of course, the result will be the same, right? It's not that they're going to change the result. But in doing the combinatorics, it's much easier to think of it this way, right? When you have already symmetrized in all the external legs in defining the vortex.
Yeah. But I'm still not certain whether this will go through for, in general, all theories.
Yeah, this will go through for all theories, as long as you symmetrize in all the external legs, right?
But this symmetrization procedure is not, I mean, for a single field, it is fine. But when we have multiple fields.
No, multiple fields, of course, you don't symmetrize, right? For multiple fields, you label the legs by, this is a chi leg, this is a phi leg, right? That's the example that we did today, right?
Yeah, so in
coupling.
Yeah. So in those cases, something like extracting the amputated Green's function, is it straightforward or I'm not sure.
Yeah, it is more or less straightforward. I mean, why not? Unless the problem could be if there's a mixing between chi and phi.
There is, right, because the coupling is containing both the terms.
Yeah, in this case, actually, there isn't. The example that I gave, because chi phi square, right? This coupling, there's a phi goes to minus phi symmetry, right? Under which phi is odd and chi is even.
I see. Okay.
So there'll be no mixing. But okay, in general, yes, indeed, there can be mixing. Okay, and in that case, you have to diagonalize, right? In that case, is G that external 2-point function that you have, right? The sigma is not a number but a matrix. Okay, imagine there are K fields which mix with each other, right?
Yeah.
Then sigma you can think of as a matrix, and now you have a K by K matrix which you have to invert.
Okay.
Okay, but otherwise the procedure is more or less straightforward.
All right.
Okay, are there other questions?
Sir,
Yes, go ahead, please.
sir, can you go to the previous page?
Previous page here. Okay.
Yes, a bit above.
Okay.
No, I think where you have written the gauge freedom, which is reflected as the absence of a naught, a zero, a dot of dot of a zero naught. Yes.
Yeah. Okay.
You say so. Since we have seen that action is gauge invariant, that is under the transformation mu goes to mu plus del mu of some lambda.
Yeah.
So f mu or any physical quantities would not depend on would be independent of this transformation.
That's right. Yes.
So yeah. So and this transformation is for all mu, that is all of the 4 components.
Yes.
So in this whole procedure, why it's the only A0 component which have this problem?
No,
I mean,
others also have this problem, right? But the point is,
I
once
mean,
A0 is
okay.
fixed, the others are fixed. You see here, let's look at the equation, right? See, once A0 has this problem, right?
Yes.
Then this is also, it's not determined, right? Once A0 is determined, this is determined, right? But it's ambiguous because A0 is ambiguous. So this is of course also ambiguous, right?
Okay.
So basically the point is, because you have only one function, lambda, right? One particular function is ambiguous, which you can take to be A0 or which you can take to be some other component of it.
Yeah, in general, this can be another function, and because of that, all the 4 components will be ambiguous.
Exactly. Right? And we see it here, right? Once A0
Yes.
becomes ambiguous, then AI also becomes ambiguous.
Okay, so we can reformulate in another way where we'll have the A0 dot equation, but ambiguity will be there for 4 components.
Okay, yeah, ambiguity will be there for all 4 components. The reason that A0 is playing a special role is because you are giving a special role to time. Okay. For the other components, right, AI, for example, if you are trying to evolve in the x1 direction, right? Let's say that you don't want to evolve in the time direction, we give the initial condition at a fixed x1, and then you want to calculate the result for other x1s, right? Then A1 will have the problem. Okay, that there'll be no del 1 A1 term in the equation of motion. So here the reason that A0 is playing a special role, right? That A0 dot is not determined is because you are trying to determine the time evolution.
Okay.
Right? That's why del 0 A0 is not there, right? The del 0 A0 is not there. Similarly, del 1 A1 is also not there, right? So if you are trying to evaluate the x1 evolution, then the problem will be coming in A1.
Oh, this is because F mu is antisymmetric and its diagonal elements are all 0.
Exactly.
So,
exactly.
Okay, and one more thing.
Yes.
You said that when we use perturbation theory, we have to choose a gauge.
Yes.
To start with.
Yes.
So, why is it so? We have to put gauge is there some?
Yeah, very naively you can see it this way, that the propagator in some sense is the inverse of the kinetic operator. Okay? Like in Klein-Gordon field, right? We had the box plus m square, right? And its inverse was the propagator, right? 1 over p square plus m square.
Yes.
Now here what happens is the kinetic operator, okay, has a zero eigenvalue. Okay? Because if mu is proportional to del mu lambda, right? The kinetic operator is identically zero. So if you naively want to proceed and try to define a propagator, right, you will find an infinite answer. Right? That's the practical way of saying why gauge fixing is necessary when you are trying to do perturbation theory. Okay? Because in perturbation theory, you use the propagator to build Feynman diagrams, right?
Okay, so it's the problem of the structure of propagator because it uses the
exactly. So the propagator will be ill-defined unless you fix a gauge. Okay? But there are approaches to gauge theories, right? Like lattice gauge theory, for example, doesn't have to fix a gauge. Okay? Because they do path integral formulation, okay? And do it not on as perturbation theory, but just evaluate on the computer in the path integral. And there you can do without gauge fixing.
Okay, because perturbation theory uses the Feynman diagram approach.
Exactly, that's right. Because perturbation theory uses Feynman diagram, so you need the propagator, and the propagator becomes ill-defined unless you fix a gauge.
Okay. Okay, thanks.
Are there other questions? Okay, so if not, we'll continue next week. So next week, I think there'll be a tutorial on Wednesday. So we'll have the regular classes on Thursday and Friday.